Good morning. So, in the last class we started discussion on design of the linear discriminant functions in cases when we do not know what is the probability density function or the nature of the probability density function of the set of training samples that are given. That is, in the cases when I do not know what is the nature of the data distribution, then I cannot have any parametric form of the probability density functions. So, even in such cases, how we can design the linear classifiers. So, we have started discussion based on that because it is a linear classifier. So, in d dimensional space, the classifier actually will be a hyperplane, and we can have an weight vector where the weight vector is actually orthogonal to the hyperplane. So, if we can find out what is the weight vector, then basically our classifier is designed, particularly when I have a 2 class problem, that is I have to differentiate between 2 classes, say omega 1 and omega 2. So, the problem that we have tried to address was something like this, that given a set of feature vectors, say x, in that case actually what we have is, if I transform this feature vector x into another vector y, the set of vectors y, where this y is obtained by appending one more dimension which is constant equal to 1 to the components of the vector x. So, if x is of the form x 1, x 2 like this up to x d, where x is a d dimensional vector, then the vector y will be of the form x 1, x 2, x d, then followed by another component which is equal to 1. So, effectively this vector y actually becomes d plus 1 dimensional vector. Okay. And let me put it as, so we are considering vectors of dimension d hat, which is nothing but d plus 1, where d is the dimensionality of the original set of vectors. Okay. So, given this type of situation, we have seen that our classifier now is of this form, that if A transpose y is greater than 0, we decide that y is from class omega 1. If it is less than 0, then we decide y belongs to class omega 2. Okay. And for design purpose, what we have done is, for all the training samples which are given from class omega 2, we have negated them, so that I have an uniform criteria that if the weight vector A properly classifies a sample, I will always have the condition that A transpose y will be greater than 0. The moment A transpose y becomes less than 0, I know, irrespective of the class from which that y has been taken, the moment I get A transpose y less than 0, I know that that y has been misclassified by the weight vector A. So, I have an uniform criteria after this negation operation, that whenever A transpose y is greater than 0, means y is properly classified for any of the vectors y. If A transpose y is less than 0, then y is misclassified. And to find out such a weight vector A, we have adopted a criteria function. So, we have said that if A is a solution vector, in that case the criteria function will be minimum. If it is not a solution vector, in that case the criteria function will be non-minimum. Okay. So, in general, if we have a criteria function, say j, which of course is a function of A, we have to put it in the function of A, because we are trying to find out the proper value of A. Okay. And then we have adopted a gradient descent procedure to converge to the proper value of A. So, the algorithm that we have adopted is, initially we assumed an iterative algorithm that A 0, which is arbitrary, and a k plus 1 was obtained from a k. A k is the weight vector in the previous iteration minus some convergence factor eta times grad of J A, where this gradient will be taken with respect to vector A. Okay. So, this is the general gradient descent algorithm, and in perceptron criteria we have defined the criteria function J P A as minus A transpose y, take the summation over all y which are misclassified by A. Okay. So, following this we had come to an algorithm following the perceptron criteria that again as in general case we start with an arbitrary weight vector A, and then every iteration A is refined following the similar algorithm, that is A k. Now, because this term is negative minus A transpose y. So, over here this will become positive. So, instead of minus it will be plus. So, it becomes A k plus eta times, where eta is the convergence rate, summation of y for all y which are misclassified. Okay. So, what we have said is that this criteria function J p will attain a value equal to 0, okay, when all the samples are properly classified by the weight vector A, otherwise it will be non-zero. Okay. So, as a result you find that J p can have a minimum value which is equal to 0, that means it has a global minimum, and because it has a global minimum. So, following this iterative procedure, iterative algorithm, we can attain that global minimum which will be equal to 0 whenever A is my solution vector. Okay. Now, you find that there is a problem over here. The problem is in terms of memory requirement for execution of this algorithm, because in all real life situations we will have thousands of training samples for supervised learning of the classifier. Okay. So, when I have thousands of training samples, obviously I will have thousands of samples which will be misclassified initially, and this says that I have to have summation of all the samples which are to be added to this vector weight vector A k. Okay. So, I need large amount of memory. So, I can have that instead of taking all the samples together, instead of considering all the samples together, I can consider sample by sample. That means, I can have a sequential version of this particular step. So, what I have is I have samples A 1, A 2. So, let me put it as superscript, not subscript. So, I have samples A 1, y 1, y 2, y 3. It continues at the kth instant. I will consider sample y k, that is the kth sample vector, okay, and we have n number of samples y n. So, what I will do is I will start with a particular weight vector, that is the initial weight vector, test this y 1 whether A transpose y 1 is greater than 0 or not. If I find that A transpose y 1 is greater than 0, I do not update, I do not modify the weight vector A. I simply pass on to the next sample y 2. So, if I find that A transpose y 2 is also greater than 0, that means the same weight vector, it properly classifies y 1, it also properly classifies y 2, right. And when I consider this, all the samples which actually belong to omega 2, they are already negated. So, I assume that all the samples which belong to y 2, they are already negated. So, in all the cases I will have single criteria decision rule that A transpose y k has to be greater than 0 if y k is properly classified by the weight vector A. Okay. Now, suppose I find that A transpose y k has become less than 0. Before that, up to y k minus 1, all the samples, for all of them A transpose y was greater than 0. So, I need not have to modify my weight vector A. So, when I find that A transpose y k has become less than 0, that means it is the kth sample, kth weight vector, kth sample that has been misclassified by the weight vector A. So, as I determine that the kth sample has been misclassified by the weight vector A, so immediately I have to update A. Okay. And for updation, I will follow the procedure same as this, but here instead of summation of y, I will have only y k. Okay. And with this modified vector, I continue with other samples. Now, if all other samples are properly classified by this modified weight vector, I need not modify the weight vector any more up to this y n, but I am not sure what happened to y 1 to y k minus 1, because y 1 to y k minus 1 was properly classified by the previous weight vector, and I have modified the weight vector when I encountered the kth sample. So, this modified weight vector I am not sure whether this will also properly classify all these previous samples or not. So, I have to try it again. And finally, the algorithm will terminate when in a single pass all the samples are properly classified by that particular weight vector. Okay. So, whenever the weight vector is modified, on that modified weight vector I have to try out all the samples. If all the samples are properly classified by a weight vector, then only I will say that my classifier has been designed, or the weight vector that I have got, that is my solution vector. Okay. So, following this, now the new algorithm will be again as before, A 0 is arbitrary, okay, and A k plus 1 that is kth sample will be A k plus eta times y k. Okay. So, now you find that summation term is no more there. So, here because we are considering sample by sample, not all the misclassified samples together. So, the memory requirement for execution of this algorithm will be much less compared to the previous version. Okay. Now, let us see that whether this ensures that the algorithm will really converge. Okay. So, that we will try to demonstrate with the help of this sequential algorithm. I will get the same result whether I consider all the samples together or I consider sample by sample. Okay. So, let us to demonstrate that, let us consider a case in 2 dimension, because that is the one I can plot on the paper. Okay. So, let me consider a case in 2 dimension. So, I will have 2 dimensional weight vector samples. Suppose the components are x 1 and x 2. Okay. And suppose I have a number of training samples. So, these are the samples which belong to class say omega 1, so arbitrary set of training samples. Okay. And suppose these are the samples which belong to class omega 2. Okay. So, these are from class omega 1 and these are from omega 2. Okay. So, as I said that to have an uniform decision rule, I negate all the samples which are given from class omega 2. Okay. So, all these samples have to be negated. So, the negated samples will be like this. I will have over here. Okay. Then okay. So, these are the negated samples. Okay. So, if this is y, this is minus y. Now, when I try to find out the weight vector, we said that the weight vector is orthogonal to the decision surface or orthogonal to the hyperplane. Now, as we are considering two dimensional case, so that hyperplane is equivalent to a straight line. Okay. Now, what are the straight lines that or the set of straight lines which actually demarcates between these two different classes omega 1 and omega 2. Okay. So, you find that I have some limiting cases. What are those limiting cases? One of the limiting case is say this one. This is one of the limiting case, because the moment this particular straight line is rotated anti-clockwise further, this sample is going to be misclassified. Okay. If I rotate it clockwise, all these samples will be properly classified. I have some zone over which, even if the straight line is rotated, all the samples are properly classified until and unless I reach this particular position. Okay. So, the moment I reach this position, if the straight line is rotated further in the clockwise direction, then this sample is going to be misclassified. Okay. Now, within this region, whatever be the position of the straight line, whatever be the orientation of the straight line is going to classify this set of samples from omega 1. Also, this set of samples from omega 2, both of these sets will be properly classified for any position of the straight line within this region. Right. Now, what is the nature of the corresponding weight vectors? We said that weight vectors are orthogonal to the hyperplanes. That means, over here the weight vectors will be normal to the straight lines. Okay. So, one limiting case of the weight vector is over here, which is orthogonal to this straight line, perpendicular to this straight line, and the other limiting case will be this, when this weight vector is perpendicular to this straight line. Okay. So, you find that I have a conical region. So, I have a conical region like this, where if the weight vector is within this conical region, I mean any weight vector within this conical region is going to serve my purpose, right. So, once I know, so this is what is my solution region, I call it the solution region. So, any weight vector within this solution region, it will classify this omega 1, all the samples in omega 1 and all the samples in omega 2 properly. So, my aim should be that when the algorithm converges, the algorithm should give me an weight vector within this solution region, that is within this conical space. Okay. Let us see how we really get it. So, I will start with some smaller number of samples for algorithm illustration. So, these are say samples from class omega 2, omega 1, and say these are samples from class omega 2. Okay. So, given this, my limiting decision boundaries, decision surfaces are, one is this, the other one is this, okay. And the corresponding, I assume that these samples to omega 2 from class omega 2, they are already negated. Okay. So, these are the negated samples, and the solution region in this situation will be this. Bounded by this conical space. This is the solution region. So, this is my dimension x 1 and this is the dimension x 2. Okay. Now, because initially we said that A 0 is arbitrary. So, I cannot ensure that the initial choice of A 0 will be within this solution region, that is the weight vector within this solution region. Let us assume that my initial weight vector, because it is arbitrarily chosen, is chosen somewhere over here. So, this is my A 0, right. When this is A 0, the initial weight vector, the decision surface which is actually defined by this A 0 is orthogonal to this. So, this one, okay, which is orthogonal to this. Now, find that when this is my decision surface, this decision surface properly classifies this sample as well as this sample. It also properly classifies all the samples which are in class omega 2, but this decision surface misclassifies these 3 samples. These 3 samples actually belong to class omega 1, but this weight vector classifies them to class omega 2. Okay. So, these are the 3 samples which are misclassified. Now, find, suppose I take the samples in a sequence, say this is my y 1. So, I initially considered this sample for testing. I found that this sample is properly classified. So, I do not modify my weight vector. Then I have considered this sample. This is also properly classified. So, I do not modify my weight vector. The third sample is possibly this one. Okay. And for this sample, I find that A transpose y has become less than 0, because this sample is misclassified. Okay. And what is my algorithm? My algorithm says A k is equal to, or let me put it as A k as is equal to A k minus 1, same the previous iteration, plus constant eta times y, which is misclassified, right. So, what it means, that this vector y will be scaled by a factor eta, and that will be added to A k minus 1. Okay. So, this is the vector y which has been misclassified. A scaled version of this will be added to this weight vector w. That means, the weight vector w will be moved in the direction of this vector y by certain fraction. Okay. So, this was my initial w. Now, say w is moved to somewhere over, or let us put it into the decision region somewhere over here. Okay. If this eta is such that the scale factor that has been imposed on y is such that the vector has been pushed into the decision region. Okay. Or suppose the vector has been pushed somewhere over here. So, it is outside the decision region. Okay. So, this was my A 0. Now, this has become the position of A 1. Now, this A 1 will properly classify this sample, this sample, this sample, but it may not properly classify this sample. If it does not classify this sample, In that case, to determine A 2, I have to add to A 1 a scaled version of this sample. Okay. Now, this is in this direction. So, this vector will be moved in the same direction of A 2, okay, by certain factor. And while doing this, you find that now it may be possible that this A 2 has come within the decision region. Okay. So, once this A 2 is pushed into the decision region, all the samples over a single pass will be properly classified by this weight vector A 2. Okay. So, effectively what I am doing is, in every pass I am pushing the weight vector in the direction of the misclassified sample by certain distance. Okay. And while doing so, I am ensuring that this weight vector will be pushed into the solution region. Okay. Now, it may so happen that the value of eta is so high, that is rate of convergence is so high, that when I am trying to come to this A 1, for this A 1 it has totally moved out of the solution region and A 1 has come somewhere over here. That is also possible if the value of eta is very high. And if A 1 is pushed over here, then you find that all these samples will be misclassified. Okay. Whether I mean all the samples in omega 1 from class 1 they will be properly classified, but all the samples from omega 2 they will be misclassified. And when the samples from omega 2 they are misclassified, actually the samples from omega 2 are on this side, not on this side. This is actually negated version. I am adding y, that is the unnegated version. So, because these samples are on this side, I will have to add the corresponding samples to this location, to this weight vector, okay, and weight vector will start moving in the reverse direction. Okay. So, finally, I will get a situation that when the weight vector will actually converge, when the algorithm converges, the weight vectors will be within the solution region. Okay. So, that means this perceptron criteria ensures that when the algorithm is terminated or converges, I actually have an weight vector within the solution region. Is it okay? Now, find that still there is some problem. What is the problem? If at convergence I get an weight vector somewhere over here, just within the solution region, or somewhere over here, which is also just within the solution region. So, still my algorithm will converge, and for these training samples I get a weight vector which properly classifies these training samples. Okay. But you remember that these training samples are just representatives, they do not cover the entire set of samples. Okay. Now, what it means, if the training sample is somewhere, if the weight vector converges somewhere over here, then actually I am getting a decision surface which is just outside this sample. Okay. If the weight vector converges here, I get a decision surface which is just outside this sample, right. So, it just barely classifies these two sets of samples, but because these are representatives, there is no guarantee that I will get other samples from this class which will be on this side, or I will get samples from this class which will be on this side. Okay. So, to minimize the risk, what I would like to have is, I would like to have a decision surface in a narrow region somewhere over here, so that the risk is minimized. Okay. If I want to do that, that means I want to restrict this solution region somewhere over here. So, I do not want to be satisfied simply by A transpose y greater than 0. If I want to constrain my solution region within a sub region of the solution region, which is well within the solution region. Okay. That means, I will be satisfied only when I get a weight vector over here. I am not satisfied if I get a weight vector over here. Okay. So, effectively what it means is that these solution vectors or these decision regions, they are pushed inside, right. And how I can ensure that? I can ensure it not by my decision rule that A transpose y greater than 0. This will be ensured by if I put some margin that A transpose y is greater than some margin B, where B is a positive constant. Okay. So, in this criteria, to decide whether this y k is classified or misclassified, I will not use A transpose y k greater than 0 to decide if it is misclassified. Rather, I will say if A transpose y k is greater than B, then it is properly classified or safely classified. If it is less than B, but greater than 0, it is properly classified, but still not safe. Okay. So, instead of having my decision rule to be A transpose y greater than 0 for proper classification, I will put the decision rule as A transpose y greater than the margin B for proper classification. Okay. And by doing that, if I take the misclassified samples, then effectively I am ensuring that I will end up with a weight vector within this restricted region. Okay. And then the classifiers that I get, those are reasonably safe. Okay. I can never say that it is absolutely safe, but they are reasonably safe given these two sets of training samples from class omega 1 and class omega 2. Is that okay? But this Perceptron criteria is not the only criteria that can be used for this linear classifier design. Then maybe there can be many other variations of this perceptron of this criteria function, and accordingly we can have different algorithms. Okay. One of the variations of the criteria function is defined like this: J R A is equal to half of A transpose y minus B square upon mod of y square, again for all y which are misclassified. This is another criteria function that can be used for getting a proper weight vector A, and this has to be minimized of course, and this is a criteria function which is called relaxation criteria. And accordingly, the algorithm that we get for minimization of this criteria function to obtain the weight vector A is called relaxation procedure. Okay. But that is also done following the same gradient descent procedure. That is, if I take the gradient of this A, this J R A, of course, this gradient is with respect to the weight vector A. Okay. This will be simply summation of A transpose y minus B upon mod of y square times y. Again this summation over all y which are misclassified. Okay. So, when I do this, again my algorithm remains the same, that is I choose A 0 arbitrarily, okay, and to decide about A k plus 1, I simply take A k plus eta times summation of this becomes B minus A transpose y, because actually it is A k minus this in gradient descent procedure upon mod of y square times y, again for all y which are misclassified. Okay. So, this is the relaxation algorithm or relaxation procedure. Okay. So, again you find that over here I have summation of this term for all the samples which are misclassified. So, again the algorithm is memory intensive. Okay. So, I can still have a sequential version of this, and the sequential version as before will be you choose a 0 arbitrarily, okay, and a k plus 1 can be obtained using the iterative procedure a k plus eta times b minus a transpose y k, that is the kth sample. Okay. And truly speaking, this is not A transpose, it is A k transpose, okay, upon mod of y k square into y k. Okay. So, again over here you consider the samples sequentially one after another. The moment I encounter a sample which is misclassified, okay, I update the weight vector A k following this updation rule. Okay. So, this is sequential version of the same relaxation procedure, right. And there may be other criteria functions as well for designing of the classifier. But one thing you must have noticed that whether I use the perceptron criteria or I use the relaxation procedure, in both these cases the convergence is guaranteed if the classes are linearly separable. Okay. Otherwise, the algorithm will never converge. There will be at least one sample at some point of time which will be misclassified. Is that okay? So, the convergence is not guaranteed. So, I can make use of these algorithms only when I know for sure that the classes are linearly separable. Otherwise, I will not get any convergence. However, if I am not sure if the classes are linearly separable or not, still I can try to design a linear classifier, but there my aim will be that whichever linear classifier I design, that will give me the minimum error. Okay. So, accordingly I can have a classifier based on minimum squared error. Okay. So, how should I go about this? You find that so far my decision rule was that if A transpose y is greater than B, I assume y is properly classified, right. So, what is my decision surface? Decision surface is A transpose y is equal to B. Okay. So, I have to get a solution to this equation A transpose y is equal to B. Okay. And this, the solution of this equation can be obtained by this minimum squared error procedure, right. So, over here you find that if I consider the ith sample, my condition will be A transpose y I is equal to B, okay. Or to be more general, let me assume that this will be B I. If for every sample I can have different components or different margins for generalization. Okay. So, for every ith sample I have such an equation, I have n number of such samples. Okay. So, I get n number of such equations. Then what I have to try to do is that I have this n number of simultaneous equations, and I have to solve this n number of simultaneous equations. Is that okay? In matrix form, it will be something like this, say y 1 0, y 1 1, y 1 2 up to y 1 d, then y 2 0, y 2 1, y 2 2, y 2 d, like this, y n 0, y n 1, y n 2 up to y n d, times a 0, a 1 up to a d, that should be equal to b 1, b 2 up to b n. Okay. So, that n number of simultaneous linear equations can be put in a matrix form like this, and in the compact form I can write it as y a is equal to b. Okay. So, you can say that what is great in it? I can as well, if y a is equal to b, I can as well get a is equal to y inverse b. Okay. But the problem is this y is not a square matrix, it is a rectangular matrix. Okay. Number of rows, which is the number equal to the number of samples, that is n, and the number of columns is d plus 1 or d hat. So, the number of rows is much less than the number of columns. Okay. So, in this case the vector A is actually over determined, and following this simple approach I cannot get an exact solution for this vector A. So, that is the major problem. So, how to go about it? How to get the solution for this vector A? So, to get the solution for this vector A, we can define an error vector. So, that error vector E is actually y A minus b. Okay. And our aim will be to get a solution for A that minimizes this error. Is that okay? So, instead of simply trying for y inverse b, we will try to get a solution A, because y is known, this is nothing but the set of training samples. Okay. B, let us assume that this is also known, that is the margin vector. Okay. So, what I have to do is I have to try to get a solution for A, which will minimize this error vector E. Okay. So, for that let us define a criteria function, which is sum of squared error. Okay. So, let me write it as J S A, which is equal to y A minus b mod square, okay, and which in the expanded form is nothing but A transpose y I minus b I square, where I varies from 1 to n. Okay. So, you compute the error for each and every sample vector, take the square of it, sum over all the samples, that gives you sum of squared error. Okay. And what I will try to do is, I will try to minimize this squared error while trying to get a solution for this weight vector A. Okay. One of the approach is obviously the gradient descent approach. Okay. You start with an initial weight vector, then go on updating it. Okay. So, the gradient of J S A with respect to A from here will be nothing but sum of into A transpose y I minus B I into y I, okay, where this I varies from 1 to n, right, which can simply be written as in the matrix form 2 y transpose, okay, into y A minus B. Okay. So, using this gradient, I can make use of the gradient descent procedure to obtain a solution for A. Otherwise, I know that when I obtain a solution, this term has to be equal to 0. Okay. This term has to be nullified. So, accordingly, I can obtain a closed form solution which is given by just by equating gradient of J S A is equal to 0, and that simply gives me, because gradient of J S A is nothing but 2 y transpose y A minus B, that has to be equated to 0. That is, this being a matrix equation, it has to be equated to a null matrix. Okay. And from here, I will get y transpose y A, y transpose y A is equal to y transpose B. Okay. And from here, I get a solution for A, which is equal to y transpose y inverse of this y transpose B. Okay. Now, over here you find that though y is a rectangular matrix of dimension n by d, okay, but y transpose y, that will be a square matrix of dimension d by d, because y is n by d. So, y transpose is d by n, y is n by d. So, d by n multiplied with n by d matrix, it becomes a square matrix. Okay. And quite often this matrix is non-singular. Okay. So, this being a square matrix, and if it is non-singular, I can find out y transpose y inverse, and this term y transpose y inverse into y transpose, this is what is known as pseudo inverse. So, I get A is equal to A plus B, where A plus is the pseudo inverse of y, and pseudo inverse is defined as y transpose y inverse into y transpose. Okay. So, this y plus, this is actually pseudo inverse of y. Okay. And you find that if y is square and non-singular, in that case this pseudo inverse will be same as regular inverse of y, that you can verify. Okay. So, I get a solution like this, a closed form solution for the weight vector A. But we said that in most of the cases this pseudo inverse exists. In most of the cases y transpose y is non-singular, it is square, and in most of the cases it is non-singular, but there is no guarantee that it will always be non-singular. Okay. But still we can find out a solution to this weight vector A following again some iterative algorithm starting from here. Okay. So, that is an algorithm which is called Wiedehoff procedure or LMS procedure, least mean square procedure. So, what is that? We have Wiedehoff or LMS procedure. So, what is this LMS procedure? again we will assume that A 0 will be chosen arbitrarily. Okay. And A k plus 1 will be A k plus y transpose into B minus y A k. Okay. So, as I said, you find that this is the gradient of our mean square error criteria. So, if I follow the gradient descent procedure to obtain the k plus first weight vector A k plus 1, it is A k minus eta times this gradient. Okay. So, which is nothing but this A k plus 1 will be equal to A k plus y transpose. So, before this if we want we can put this convergence state eta. So, it will be A k plus eta times y transpose. Initially it was negative. So, this y a minus b will now be b minus y a, because I have made it positive. So, this is eta y transpose b minus y a k. Okay. Now, find that over here all the samples, all the training samples are considered together, because it is a matrix equation. Okay. So, the same problem of memory requirement, it will require large amount of memory for execution of this algorithm. So, to solve that, again I can have a sequential version of the same algorithm, and the sequential version is similar to what we have done before. That is, we assume this A 0 to be arbitrary, okay, and A k plus 1 will be given by A k plus eta times b k minus A transpose k y k times y k. Okay. So, this is the sequential version of the same least mean square procedure, which makes use of the iterative technique to find out the weight vector A. Is that okay? So, over here you find that since I do not have to find out the inverse of the matrices, so this guarantees that I will always get a solution, and my aim is to have a solution. Obviously, I cannot have a perfect solution, because I have not assumed the linear separability. But what I wanted to do is, I wanted to get a vector which will give me a linear classifier, and that linear classifier will ensure that your least mean square error will be minimum. Okay. So, I will stop here today. Next day we will continue with other topics.